welcome to the head-on introduction to object-oriented analysis, design and programming. My name is Tobias Olsson and this work is licensed under the Creative Commons Attribution Share Alike. We have a problem in software as it is in many ways becoming more and more complex and powerful. Software is not a physical object that we can intuitively reason about. It is not really bound by natural laws. Laypersons cannot really understand software easily as they can many physical objects. Building a software is not like building a single car. It is more like building a factory that we can then easily change to produce the cars that we want. The step from an idea in someone's head to a stream of binary digits that can be understood by a computer is quite large, and looking at the stream of ones and zeros, you can seldom understand the exact purpose of the idea and the problem to be solved. This is called the semantic gap problem. Software is everywhere, and it is an integral part of modern society and business. As software developers, we need to understand not only technical programming aspects, but rather the actual problems and opportunities in other areas. We have a constant stream of new and more advanced technologies and algorithms. For example, machine learning and cloud computing. Modern software is distributed and connected. This adds to the complexity. Just being able to code well is not enough. We need a way to think about problems and dividing a solution in subparts that can be understood, managed and distributed to as many stakeholders as possible. This is a bit of a problem to sufficiently demonstrate in education as we have limited time and resources. We tend to focus on small, well-defined toy problems that are solved in a short time frame and with specific technologies. For that reason, some practices can seem redundant and unnecessary, as you, for example, do not need to live with a poor solution for very long as a student. To tackle the software complexity problem, the first step is to start working in a non-chaotic way. A simple development process is the what, how, do, check process. First, we need to work together with customers and end users to understand what is wanted, what the problem is, and quickly find out things that are unclear or misunderstood. This is the what step. Second, we need to use our technical expertise to find out how we can construct reasonable solutions and divide the solutions in parts that we can manage, parts that give value to end users and opportunity for early feedback, constructed in such a way that they facilitate change. Third, we need to be able to work together in parallel and focus our expertise as efficiently as possible. We also need to rely on pre-built parts to be able to implement the solution. This is the do step. Finally, we need to efficiently show that the implementation is working as intended and that it is what the end user wants. We need to easily find the root causes of problems. This is the check step. With some nicer words, these are the basic steps of any software development process: requirements and analysis, design, implementation, and test. Object orientation revolves around the concept of the object. This may sound very strange right now, but as we progress, it will hopefully become more clear. Basically, an object is the unity of behavior and the data needed to support that behavior. Objects communicate with each other via sending messages and can thus collaborate to create the desired system behavior. A system itself can be considered an object at a macro scale. It encapsulates some data and the behavior and communicates with other systems using messages, compared to, for example, microservices. Objects provide a way to manage the software complexity that has analogies to how we as humans try to cope with complexity in our everyday lives. As humans, we often try to be as abstract as possible. For example, when requesting a cup of coffee from a friend, we say, "Could you get me a cup of coffee with milk, please?" We do not specify exactly how the coffee is made, the kind of jar, nor the place to get the coffee from. We talk about what we want, not how it is done. With a nicer word, this is called abstraction. In real life, you are responsible for handling your own stuff. For example, I could ask you to change your name to Alan Turing, but ultimately it is you that decide if you want to do that or not. If a friend asks me to borrow him $10, I do not give him my wallet. In the same way, an object is responsible for the data it contains, and encapsulation means that no other object should be able to know or manipulate the data without involving the object. Whole part hierarchies means that many objects in real life are composed of other objects. For example, a car is a pretty complex object, but we can use it at the car level of abstraction quite easily. Looking at the car in detail, however, we find that it is composed of many more objects, like brakes, engine, gearbox, etc. Looking at the brakes, they in turn are composed of even smaller objects. Together these collaborate to create a more meaningful whole. That is a car that you can drive, without the need to really understand or even know about the smaller parts. Again, abstraction and encapsulation. As humans, we tend to reason much in hierarchies. Consider, for example, a discount in a store. We all know basically how discounts work. You get some cheaper price if the condition of the discounts are fulfilled. However, the details are different for different kinds of discounts. For example, one type of discount may be a 5% discount on the whole amount if the amount exceeds $50. Another type of discount could be that you get one item free if you buy 3 or more items of a particular kind. By having general knowledge about discounts, we implicitly know something about all discounts. They will reduce the price you pay. However, the exact behavior of the discounts are special for every type of discount. Object orientation lets us express such hierarchies and lets us specify the exceptions so that we can have both general behavior and add special behavior when needed. Object orientation provides a way to perform the what, how, do steps of the process that is coherent and provides a shared vocabulary and understanding of the problem from end user to developer. It is also important to realize that you can create perfectly bad systems while using object orientation. It's basically a tool like any other, and you should train using it and know when and how to apply it to gain the best effects of it. Now for a bit of a disclaimer. Professional developers do all of these things that we are talking about, but there is of course a difference in how professional developers do things compared to beginners. Basically, what professional developers do is always not clearly visible. It's processes that goes on in people's heads, scribbles on post-its or notebooks or whiteboards, knowledge that exists in organizations, etc. The underlying principles apply, but the exact process is of course different. For example, we will often create very detailed designs, and this is not realistic to do for an entire system with experienced developers. But we need to understand the basics and crawl before we can run. Alright, to make this presentation a more heads-on approach, let's just take a look at an example of what you can achieve with object-oriented analysis and design. And to start off that process, we need to have a requirement. During this time, I will also ask you to pause the video and maybe think a little bit for yourself before moving on, just to compare how you think and how you can think using object orientation. So, take a moment and read the requirement and try to form a mental model of what parts are involved in this simple dice game here. One thing you can notice is that we have a few central concepts. We have the dice game itself, we have the dice, and we have the player. The player does something in the game, he rolls the dice, and we collect the sum of the dice and we see if we win or not. So we have some kind of a static side and dynamic side. We have the items in the game, the entities of the game, and we have the stuff that happens to the entities. So let's start by looking at the entities. The requirement is actually quite vague in some respects. We know that there are dices and we know that there is a player and a dice game, but we actually don't know how many dices we have or how many sides these dices have. We kind of like assume that they are 6-sided dices perhaps, and that we have 2 of them, since the sum should be able to reach 7 at least. But such assumptions can you really not make, but it's very easy to do that automatically. So when you are faced with the requirement, you really need to understand it so that you don't bring your own assumptions into it too much. So if we look at this structure, we make a visual model over it, and it's the simplest kind of notation we can imagine: boxes and lines. And we have these three main entities here: the dice game, the player, and the dice. And we put a line between the entities so that we can show visually the important relations here. So we know that the player plays the dice game. The dice game has or maybe contains 2 dices. The dice has a value between 1 and 6. So using this, we can understand the requirement better. We know the main parts that are involved and how they are related. We have also added a little bit of information here. We have found out that our requirement was lacking in some respects because we did not know that there were 2 dices, and we did not know that there were 6 sides to these dices. In reality, of course, you need to go back to the person that stated the requirement and find out if your assumptions are correct. And actually, a model like this is something that everyone can understand, right? It's not some magic, very hard to understand visual model. It's easy to understand. You can show it to anyone and they will probably get it. So you can get early feedback from end users, from customers. Again, this was the static part that tells what entities are involved and how are they related. If we look at the requirement text, the focus here is a little bit more on actions. What is happening, the behavior of the system, what should happen in different situations. So we start off by rolling the dice, we look at the result, we have some kind of a winning condition here. So requirement focus more on dynamic, what happens in different situations. This diagram here focus more on the static part, what items are involved, what entities are involved, and how they are related. This is a good distinction to have in general when you do modeling. Some parts are good at conveying static information, others are good at conveying dynamic information. So let's move a little bit deeper into this model. So what should happen here with these entities when we play the game? We now start designing, and by looking at the requirement and the analysis, the structure, we can find out that we have a number of objects here. We have a player object, we have the dice game object, and we have 2 dice objects, D1 and D2. For the sake of the diagramming, we also have the program object that actually starts stuff. So when you run the program, the first thing that is happening is that the program object is created, and then we can start the actual behavior of the system, of the game. So the first thing that happens is that the program sends a message to the player object. Now you should have some fun with this dice game. And after that, the player object tells the dice game, okay, let's play. The dice game rolls the first dice and then rolls the second dice. Then he starts collecting the sum, gets the value from the first dice, and gets the value from the second dice, and returns true or false based on this sum. When the player object gets this message back from playing, he can then output either win or lose. So basically, we now have the dynamic part of the design done. We know what objects are involved. We know what type these objects have. We know the messages they send to each other and what should actually happen to fulfill this requirement. Last but not least, we do the structure as a design. From the dynamic part, we can see that we have a dice game class. We also have this in the analysis, and we also have this in the requirements. We know that the dice game needs to have be able to receive a message called play, and we know that that message should return a Boolean value. We know that the dice game contains two dices, D1 and D2. We know that they have a value. We know that we can roll them, and we know that we can get the value from the dice. We also know that we have a player object that uses the dice game to play and can receive the have fun message and output something. Basically, what we have done here is that we have looked at the requirements and the analysis from a dynamic perspective in the requirement and from a static perspective in the analysis. We have looked at the design from a dynamic perspective in this diagram called a sequence diagram, and we have looked at this design from a structural perspective in a class diagram. Now it's time to implement. And then we should of course use the design we have constructed as the starting point. So this is basically the first exercise. I will present the code for this step a little bit later, but you should of course try to do this yourself first before moving on. You should have the program class with the main method. The associations that we saw, these arrows here are called associations with the role name D1 and D2. They are simply implemented as member variables in the dice game. So in our dice game class, we have two member variables here called D1 and D2 of type dice. And finally, we can use math random to generate a random number in the dices when we roll them. So I hope you took some time to implement the dice game, and this is a suggested solution to that with the implementation of the dice, the player, and the dice game classes. And as you can see, we have a shared vocabulary used throughout the requirements, analysis, and design and implementation. In the implementation, we still have dices, we still have players, we have dice game. We can trace this back to the requirements themselves. And this means that end users can give early feedback and possibly even understand the implementation. It also gives the benefit of developers that understand the requirements or the domain can easily understand the design and implementation. In this example, we can see an abstraction. The user of the dice game, the play class, does not need to worry about what goes on inside the game. You just ask the game to play and get the result. The user does not tell the game exactly what to do. The dice game does not know what goes on inside the dice. For example, how many sides the dice has. We can see an example of encapsulation. The user of the dice game class cannot manipulate the internal state of the game. And we can see an example of the whole part hierarchy. The whole is the dice game and the parts are the dices. We could also easily divide this implementation into three developers. One developer implements the dice game, one implements the player, and one implements the dice. Now we will take a look at some exercises that you do on your own, and we will look at these in detail later in a later session and discuss and implement them. So of course users are not happy with the results. The printout is not what they expected. They don't just want to see win or lose, they want to see an exact dice value. So I received a 3 and a 5, for example. So we should design and implement a solution for this. You should use the existing classes and motivate your decisions. Exercise number 3. The management of our gaming company has seen a new business opportunity for these wonderful dice games. They would like to have games that can have different number of dices, so maybe 5 dices, and also have different number of sides for the dices. Also, the winning number should be changeable, so maybe one game should be played with 3 dices and have the winning condition 9 instead of 7. So we should design and implement a solution for this using the existing classes and motivate the decisions we make. And the last exercise, number 4, is a little bit more advanced, and it requires you to read ahead a little bit. So it uses things that we have not really discussed yet. But anyway, you're free to do that, of course. So our game designer has thought up a new variation of the game. In the case of a player loss, one of the dice should be re-rolled, effectively increasing the chance of winning. So you should design and implement a solution. You should add a new class. The original game should still be playable, and this new variation should also be an option to have in the implementation, so that we can sell 2 types of dice games constructed basically from the same classes. Alright, so I hope you work on these exercises, and I hope to see you soon.